The class NP. There is a wide array of decision problems for which no polynomial time algorithm is known. To be more precise, there are languages L for which there is no polynomial time algorithm known to test whether x is an L for an arbitrary input x. Quite often, there is a weaker algorithm which will not decide whether x is an L or not, but if someone claims that x is an L for a specific reason, the algorithm will verify that reasoning in polynomial time and decide whether that reasoning is correct. If it is, then x is an L. If not, then it does not follow that x is not an L, since it could still be that x is an L for some other reason. For instance, let L be the set of all pairs S, M, so that S is a set of positive integers that have a subset T, so that the sum of the elements of T is M. Now let x equals to a t be a pair so that a is a set of positive integers, t is a positive integer, and let us see that we can say about the membership of x in L. We could certainly take all 2 to the size of a subsets of a and check if any of those have some t, but that would take more than a polynomial amount of time. Indeed, 2 to the size of a is an exponential function of the size of the input. On the other hand, if someone claims that a certain subset, b which is subset equals to a, has some t, then we can verify that claim in big O of n steps by simply taking the sum of all elements of b. Of course, if the claim turns out to be false, we are out of luck, since it could well be that x in L thanks to some other subset, b prime, which is subset equals to a. This set of decision problems, that is, the problems for which we can verify, but not necessarily test, membership in polynomial time, turns out to be extremely important. This warrants the following formal definition. Definition 15.5. We say that a language L is in NP if there exists a positive integer k and a Turing machine T, so that the following hold. For each x in L, there exists a witness W of x, so that when T is given input x, W of x, it will recognize that x in L in big O of n to the k time. For each x not in L, no such witness exists. That is, no matter what input x, W prime of x we get to T, we cannot trick T into falsely saying that x is in L. In other words, L is in NP if witnesses for the claim that x in L can be verified in polynomial time, but not necessarily found in polynomial time. We point out that the witness is often called a certificate. So the introductory example of this subsection says that the language of pairs S, M, where S is a set of positive integers that has a subset summing to M, is in NP. This is actually a version of the well-known decision problem called the subset sum problem. We will take a second look at other versions of this problem shortly. Let us consider a few other classic examples. Example 18.6. Let L be the language of all undirected graphs that have a Hamiltonian cycle. Then L is in NP. Solution: and order the list v1, v2, v3 until vn of vertices of G can play the role of the witness W of G. Then all we need is to check whether v1, v2 is an H, v2, v3 is an H, and so on up to vn minus 1 vn and at the end vn v1. This means that a Turing machine T only needs to check the existence of n h's, as the head of T never needs to move more than n square cells between two checks. T can be verified in big O of n cube time whether v1, v2, v3 until vn v1 is a Hamiltonian cycle. Example 18.7. Let L be the language of all pairs of simple graphs GH so that G is isomorphic to P. Then L is in MP. Solution that bijection F, which maps from V of G to V of H, can play the role of the witness W of GH. Then all that a Turing machine T needs to do is to check whether it holds for all uv in V of G, that if uv is an edge, then f of u, f of v is an edge. As this means checking at n choose 2, which is equals to big O of n squared h's, and the head of t never travels more than big O of n squared cells between two checks, our statement is proved. The following proposition compares the two complexity classes we defined so far. Proposition 18.8. We have P, which is a subset equals to MP. Proof that if L is in P, then there exists a Turing machine T that can test the membership in L in polynomial time. So if we give input x, W of x to T, then T can simply ignore W of x and can still verify x in L in polynomial time. At this point, it seems very natural to ask whether the containment in proposition 18.8 is strict. Question 18.9. Does the equality P equals to MP hold? This turns out to be one of the most intriguing open problems in mathematics today, and probably the single most intriguing open problem of theoretical computer science. It is one of the 7 Millennium Prize problems. These are 7 particularly difficult open problems designated by the Clay Mathematics Institute in Cambridge, MA in 2000. There is a $1 million prize offered for the solution of each of them. The interested reader can learn more about these problems in the notes section of this chapter. It may sound very surprising that this question 18.9 is still open. After all, verifying a witness seems to be a much simpler task than finding one. However, there are several other points to consider. First, for P to be equal to BMP, we would not need a Turing machine T that can test the membership as fast as another machine T prime can verify membership. It would be enough to have T test the membership in big O of n to the 10,000 time, while T prime could verify membership in big O of n time. Second, in order to prove that P is not equal to MP, one would need to find a language L in MP so that L is not in P. And how do you prove that a certain language is not in P? There are other methods that could possibly be used to find the answer to question 18.9. We will mention a few of them in the rest of this section.